Hi guys, how you doing? Welcome to your first video lesson. We will meet at some point electronically, and I will post information on Canvas in the form of announcements or something so you know what's going on. I have some information about the AP exams. We have two chapters that we've got to cover in addition to this final related rates bit. In order to get ready for the AP exam, if you intend to take the exam. Um, I'll get more information to you as I know what message the school wants you all to have. So for today, we are going to go through the related rates. I'm going to make the videos in little clips so you can do a little bit at a time. You are going to have the assignment from Albert as was originally planned. We'll also do the related rates worksheet as was originally planned. And then I'll let you know what's coming after that as I figure out how to manage this new process. So just so you know, you might want to pause the video. I am going to post skeleton notes that go with the video lessons if I don't already have them for you. And so I have created just a real simple skeleton note for this related rates lesson. And it is just on Canvas in the chapter that we're on, the applications of derivatives. So if you want to print that and take your notes that way, pause the video, print your notes, and come back. If you don't want to print the skeleton notes, then still have out your notebook paper and take notes just like you always would. Because if you watch but don't write things down, nothing's going to stick. And so it's going to be easier for you when you're checking back and forth to actually look at what you've written rather than trying to come back to this video multiple times. So what are related rates? Well, related rates just means two things or three things perhaps that are changing at the same time. So for instance, if you can imagine that I'm blowing up a balloon that would be in the shape of a sphere once it's completely inflated, that each time I puff more air into the balloon, the radius of the sphere is increasing. Well, at the same time, the volume of air inside the balloon is increasing. And at the same time, you might even think the surface area of the sphere is increasing. Well, all of those are related to each other. The radius increases, the volume increases. Those are just simply related rates. So the related rates are usually with respect to time. And you will see me work some problems. Now, I'm going to start out really simple, but most related rates problems come down to you starting with a formula that you know. And it might just be the Pythagorean theorem, or it might be a volume formula or a surface area formula, just like you were using on the optimization problems that you did before the break. It might be you writing down the Pythagorean theorem. It might be that you're using basic right triangle trig and saying that sine theta equals opposite over hypotenuse and going from there. So let's do a very introductory problem first. And this one's easy because I'm straight up giving you the equation. So if you think about the graph of y equals tangent x, and it's not even necessary that you draw this, but I know that tangent x is sine over cosine, and it has its roots where sine's equal to 0. That's not where I meant to put that, which is at 0 in the pi's, and its vertical asymptotes, that's not where that was supposed to go, its vertical asymptotes at pi over 2 and negative pi over 2. And if you can imagine that you've got some little point here that maybe starts right here and over time it's moving. So the next time you check it, it's there. The next time you check it, it's there. The next time you check it, it's there. But this point's just moving along the curve. So I know that right when the point is at x equals negative pi over 4 in the graph, that the rate at which it's moving from left to right is 2 centimeters per second. The rate at which it's moving from left to right is dx dt. That's its change in its x position with respect to time. Well, what I want to know is dy dt. Well, dy dt is the rate at which it's moving from low to high at that point in time. So this is an easy problem because all you do is you start out with the equation y equals tangent x, and I'm going to take the derivative of both sides of the equation, but not with respect to x like you're used to, but with respect to y. So I need to think of this as almost like an implicit differentiation problem. So remember, I'm going to erase this, but let me just remind you, if you had like x squared plus y squared equals 4, this is a basic implicit differentiation problem. And we would say, oh, okay, so it's 2x, and then I initially said look at it as dx plus 2y times dy dx equals the derivative of 4, which is 0. And then you got to where you just said 2x plus 2y y prime equals 0, and then you isolated y prime. It's kind of the same thing, but now what we would do is differentiate everything with respect to t. So I would say, well, the derivative of x squared is 2x times the derivative of x with respect to t. So you're not going to have 1 there. The dx dt is going to be in the problem still. And the derivative of y squared is 2y times the derivative of y itself with respect to t. And the derivative of 4 is still 0. And you're going to have information to plug in for dx dt, and you'll find dy dt, or vice versa, depending on the word problem. So that's kind of what we're doing. It's like an implicit differentiation problem, very, very similar. And you're still going to have to sometimes use product rule, quotient rule, chain rule, those kinds of things, but we're going to try to avoid that. So if I look at my current problem, I'm going to say, well, the derivative of y is 1 times the derivative of y with respect to t. And the derivative of tangent x is secant squared x times the derivative of x with respect to t. So now what we do is we look back at the problem and we plug in what we can. Well, dy dt is what I want, so I'm going to show, because I've already underlined that in blue, I'll color code for just a minute. Dx dt was given, so it was given as 2 centimeters per second, so I'm just going to plug in 2 right there. Now, secant squared x, I need to do something with. But guys, it tells us x is negative pi over 4 at that moment in time. We're going to talk more about a general formula versus a time-specific formula. But at that moment in time, I'm going to say, oh, well, that's secant. Let me see if I can get this to right where I want it to. Secant of negative pi over 4. And remember, secant squared means to take that secant value and square the whole thing. So now all I have to do is work this out. So we're starting out with a very, very basic problem, just so you kind of see how the mechanics play out. So just remember, I'm going to write more initially because I got to get you back into thinking about things. But remember, on your 45, 45, 90 triangle, the sides are 1, 1 square root of 2. And if you look at secant of this 45-degree angle, I know what's the square root of 2 over 1. So secant of 45 is the square root of 2 over 1, or the square root of 2. And remember, since I've got negative pi over 4, remember, negative pi over 4 just means the angle rotates into the 4th quadrant. And in the 4th quadrant, according to all students take calculus, cosine and secant would be positive. So I'm going to say secant of negative pi over 4 is the square root of 2. But remember, it's secant squared, so I square that value times 2. Well, guys, that means the square root of 2 squared is 2 times another 2 is 4. And now I need to make sure I always add units. So the units are always, like if the numerical value of the answer is worth 1 point, the units are also worth a point. And we'll talk about how they score that on the AP exam. But I'm going to say, well, if x is moving from left to right in centimeters per second, then so is y. So this is going to have to be centimeters per second as well. If it was an area problem, I would say, oh, if dxt is centimeters per second, then area would be centimeters squared per second, since we measure area in square units. Let's do one more that's pretty straightforward, and we'll take a video break. So on this one, a pebble's dropped into a calm pond, causing ripples that form concentric circles. So you know what that looks like is the circle will spread outward. And as the circle's radius grows, we could say the area of the circle grows. So the radius of the outer ripple is increasing at a constant rate of 1 foot per second. All right, so I'm going to suggest you get used to saying, oh, wait a minute, the constant rate of 1 foot per second, that's telling me the rate at which the radius is going. So in math language, that's giving me dr dt. So 1 foot per second. And I'm going to try to start making notes of what I've got and then what I need, and it'll help me focus my equations. At what rate is the total area of the disturbed water changing? So at what rate is the total area changing? All right, so it's asking for dA dt, that rate at which the area changes with respect to time. So that's your question mark. Now I already know it's going to be measured in feet squared per second, because if the radius is in feet, the area is in feet squared. So then it gives me some time specific values. So my first time specific value is r equals 4. So this isn't a general value. And then I'll also have at r equals 6. Now, here's the basic idea. I've got dr dt, I want dA dt. That lets me know that I need to write an equation for a circle that relates area and radius. Well, that's easy. I know that the area of a circle, I'm going to erase that and try to write where I meant to, is pi r squared. So then I've got area and radius in the same equation. So what I want to do is take the derivative of both sides. So I'm going to have dA dt. Now if I take the derivative of the right-hand side, where remember r is the only variable, pi is not a variable, then I'm going to get 2 pi r, but then I have to say times the derivative of radius with respect to time. Now listen, this is really important. You cannot plug in time-specific values until after taking derivatives. If you've got a number that you know that's general, that doesn't change with respect to time, you can plug those in before you take the derivative. But anything time-specific only goes in after. So notice that one thing I can do is I can go ahead and say, well, more generally, dA dt equals 2 pi r, and then times dr dt, or dr dt. Well, dr dt is 1. So now I have a more general formula that dA dt is just going to be 2 pi r. So I can answer 2 time-specific questions. I'm going to say when r equals 4, dA dt equals 2 pi times 4, so that is 8 pi. Now what is the 8 pi? So I'm saying, oh, the area of the circle is changing at a rate of 8 pi feet squared per second. So as the radius of the circle is increasing, the amount of area that the circle encloses in the water is also increasing. But look, when r equals 6, dA dt equals 2 pi r, so that's 12 pi feet squared per second. So it turns out at the moment in time when the radius of the circle is 6, the area of the circle is increasing at a rate of 12 pi feet squared per second. So the bigger the circle you have, the faster or the greater the amount of change in the area at that moment in time. So that's what we've got there. Now I'm going to take a break because I'm still testing my videos, and we will pick back up with video number 2 and start with problem number 3 in just a moment.